Hi, my name is Charlie Turcott. I represent the Dale Prentice Company in West Michigan. Today I'm going to be talking about dust explosion hazards. We're going to identify what they are, where they exist, and then we're going to talk about how they're protected against. The Dale Prentice Company is a process safety and automation firm established in Detroit in 1926. Today we have locations and facilities across the Midwest and the Rocky Mountains. So we'll go through important definitions and design parameters. We'll talk about why we protect the way we do and the historical reasons for that. We'll go through the relevant codes and standards. We'll talk about dust hazard analysis, what that process is and why it's important. And we'll also talk about common devices that are used. Many people are familiar with the fire triangle. You need an ignition source, fuel, and oxygen. So a dust explosion is a little bit different. There's two additional conditions. The dust has to be dispersed in the air, and it has to be in an enclosure, a confinement. There are a lot of definitions that pertain to this field, but some of the most important would be the AHJ. That's the organization or organizations that approve processes based on relevant codes and standards. An air material separator, most often a dust collector. It's a device that separates air and solid dust. Dust hazard analysis is a systematic review used to identify and evaluate the potential fire, flash fire, or explosion hazards associated with a combustible solid. A deflagration is an explosion. It's a technical term for an explosion, and all it means is that the explosion is traveling below the speed of sound. A detonation is similar, but instead of subsonic, you're at sonic or supersonic speeds. Pmax is the maximum pressure generated by a combustible dust cloud in an enclosure. So if you left it uncontrolled, how high would the pressure get? And then KST is the rate at which pressure builds after a dust cloud is ignited. And here's a little graph that just kind of shows that. So these events are very quick. It's usually just a few milliseconds. The slope of that curve right there is analogous to KST. KST actually depends on volume as well, but it's the rate at which pressure goes up, and then at some point you hit a maximum pressure. So there is a difference between a dust explosion and a dust fire. Fires can cause explosions given the right conditions, but they're two different situations and they require different protection methods. It's also important to know that explosions can cause fires or other explosions. A good way to think about it, a fire, like a log, there's not a lot of surface area exposed, it burns slowly, and then a firework, all that metal dust inside the firework is dispersed in the air and it burns all at once in a big boom. It's much more violent and it's quick. So how's the field developed? There's actually a very recent example of a dust explosion, and it's probably the most often cited industrial disaster for combustible dust hazards. So in 2008, the Imperial Sugar Refinery in Georgia exploded. 14 people were killed, 36 were injured. And one of the main reasons there was so much damage is because poor housekeeping had led to accumulation of sugar dust on equipment, and when the initial explosion happened, all that dust got shook loose and then ignited and the building exploded. The building acted as a giant enclosure. You can go to the U.S. Chemical Safety Board's YouTube or website if you want to learn more about that. Even though that's the most commonly cited example, dust explosions aren't by any means new, particularly at grain elevators and mills. Today, there's a lot more processes that are looked at. A few examples: plastics, agricultural, pharmaceutical, metal fabrication, food and beverage, any industry where the chemistry of the material and the conditions are right, you could have a dust hazard. So here are the relevant codes and standards, and I've laid them out this way just to show that they are all connected. The fundamentals of dust explosions and preventing them, that's contained in NFPA 652 and 654. NFPA 68 and 69 go through what can you use to prevent an explosion in a dust collector, and how do you keep that explosion from traveling to other pieces of equipment. And then 61, 484, and 664 are all industry-specific standards, so industry or material. So what are the steps in the DHA process? Step number one, you need to test the dust to know if it's combustible. Now, this is a service we offer. We send samples down to the Fike lab in Blue Springs, Missouri. Step two in the DHA, you need to evaluate every process component. So that includes big pieces of process equipment like cyclones, but you also need to be looking at the ductwork that connects those pieces of equipment, because your deflagration could start anywhere and it can travel anywhere that's connected. If you want an outline and examples of DHAs, you can look at NFPA 652. Chapter 7 gives an outline, and then Annex B goes through examples. The last step in the DHA process is developing a mitigation and protection strategy. Now, this is where our business comes in. So what's the scope of our work? Well, if you look at NFPA 652, there's this excerpt right at the very beginning. A basis for safety embedded in each of those standards requires the fuel, in this case the dust, to be managed, ignition sources to be controlled, and impact from an explosion to be limited through construction, protection, isolation, and housekeeping. So Fike is a manufacturer that builds protection and isolation equipment, and we help design and consult with end users. So there's different ways of doing this. One of them is with an active suppression system. What that is a pressure detector, and then there's a high pressure canister, and you can see those little white canisters. They're filled with an inert material that displaces the explosion. So when the pressure detector detects an abnormal condition, it shoots in this inert material and it stops the explosion from propagating. There's other ways of doing it. You can see those stainless steel rectangles on these blue dust collectors. Those are explosion vents. When there's a deflagration in those enclosures, all those are going to do are open at a predetermined pressure and allow excess pressure to be relieved, instead of having the enclosure itself yield because of the pressure. So what you get is a big fireball shooting out instead of the metal completely being destroyed and shooting shrapnel and potentially injuring and killing someone. All these pieces of equipment, they do the same thing. So you don't want pressure to exceed a predetermined amount. You don't want it to destroy your equipment, and you don't want the explosion to spread to other pieces of equipment. Thanks for your time. I hope you learned something, and please refer to our other trainings.